From continuity equation, we defined the stream function psi, and from psi we wrote it down in two-dimensional motion, the components of u and v in the rectangular coordinates, as is the normal procedure. But sometimes, due to the geometry of the fluid field, it is convenient sometimes to work with the polar coordinates, and the polar coordinates could be, of course, in three-dimensional form, in two-dimensional form, in spherical, and the polar coordinates can be, as all of you would be familiar when you were studying multi-variable calculus, that we used to transfer the rectangular coordinates into cylindrical polar coordinates and spherical polar coordinates in 2 and 3 dimensions. In the same way here, depending upon the geometry of the flow field, it's very convenient to work with the stream function in terms of cylindrical coordinates in 2 dimension or 3 dimension, whatever the situation is, according to the situation that is required. So if the equation is the continuity equation in the rectangular form, which is divergence of V is equal to 0, this is for steady flows, incompressible flows, and we write it in rectangular coordinates as du by dx plus dv by dy equal to 0. And as we are familiar, when we transform these rectangular coordinates, we can write them in the form that has been shown to us here. Now this is when we are writing it in polar coordinates, and this is when the flow field is axisymmetric. I will just show you through the diagram also the difference between the two. For example, here this is a axisymmetric picture, a flow field, and suppose this is a body, but you can see that the motion, rather than angular, is symmetric about this line. And if we let this line to be z, then the motion, then there is a rotational symmetry that is existing, and so is axisymmetric. And therefore the rectangular coordinates, you can see if this is x, this is y, and the third, this one is z coordinate. These are 3 mutually perpendicular coordinates, and whichever we want to choose for convenience of our mathematical work, then in such a form, and if the flow is taking place across such a body, then it is convenient that we try to see the motion in the axisymmetric direction. uz will be the velocity in the z direction as indicated here, and ur, which is in the radial direction. And of course the motion that is taking place in the radial direction will be u of theta. So these are the things depending upon how the geometry is, how the flow field is. And similarly for this, we try to consider simple example as we did earlier in rectangular coordinates. Consider a line vortex defined as a steady planar incompressible flow in which the velocity components are ur equal to 0 and u theta equal to k over r, where k is a constant. The flow is represented in a figure that we show in a minute. Derive an expression for the stream function psi r theta and prove that the streamlines are circles. So this is the question. The flow field is given to us. The radial component has been given to be 0, whereas the angular component is inversely proportional to radius. So the velocity component u theta decreases as r increases, but it becomes almost too much when it increases as the r decreases, because k is simply a constant, therefore u theta is proportional to sort of 1 by r. R is the radius. Now by writing it in terms of the cylindrical coordinates as we have just written, the value d psi by dr, which will be the theta u theta component of the velocity that has been given to us, is minus k over r. So by integrating with respect to r, we obtain this. F is constant of integration, and we just, to be careful, we want it to be a function of theta. Maybe there may be some theta occurring there, or maybe it may be a absolute constant. We will see when we substitute the values of the constant. Now we use the other component, the radial component. When we obtain the radial component through this equation is equal to this one, and we integrate it with respect to r, we will have f of theta to be equal to 0, f prime of theta to be equal to 0, and therefore the value of f of theta turns out to be an absolute constant. So this f of theta can be replaced by this constant, and psi is therefore equal to minus k natural log of r plus some constant c. And we have done the first part, that is, we have determined the value of psi, and then we have to draw the curves for psi. The curves for psi have to be obtained by setting r some constant value. As we keep changing, keep giving r different values, different constant values, we will be having different plots for psi. And for a large number of points, we can produce a diagram that will depict the velocity field given by this function psi is equal to this, or as proposed in the question. From this, we can easily obtain r to be equal to this. Keep changing, keep giving different values to r, we keep finding different values for psi. And you can see that they have shown here that k is equal to this much if c is 0, and psi, the range of psi is from 0 to 22. And it's plotted here. You can see this diagram, that the streamlines look like this. Away from the origin, each streamline is away, it looks at a distance from the nearby streamline. The velocity field, although it's moving in a circular motion, but there is a clear distance between the 2 points. But as it narrows down, as it comes to 0, you can see that the velocity is really increasing, and the streamlines are also coming very close to each other.